Hi everyone, welcome back after the break. So, in the last half of the lecture, we talked about the fundamental theorem of arithmetic, which is one of the grand basic theorems of prime numbers. That you can use prime numbers to um, figure out to figure out a different way of writing out numbers as these factorizations, as using just multiplication and the prime numbers as building blocks. But now, what are all the various ways that we can use this to make some kinds of computation easier? And, well, some kinds of computation will be harder, but we're not going to talk about that so much. So, we're going to make some types of computations easier, and the basic one is, of course, multiplication is going to be a lot easier if you have a prime factorization. Because multiple prime factorizations are, well, intrinsically tied to multiplication. They're the multiplicative building blocks of everything. And so it turns out that when you multiply things in the prime factorization, you just need to add together the exponents. So let's do that. So let's say that 33,880 is equal to, I'll just go ahead and tell you the prime factorization. Finding these can be a little bit hard. So 2 cubed times 5 times 7 times 11 squared. And 31,350 is equal to 2 times 3 times 5 squared times 11 times 19. Well, using the prime factorization, we can rewrite the product. So 33,880 times 31,350 is, of course, equal to, we can substitute things in. So we have 2 cubed times 5 times 7 times 11 squared times 2 times 3 times 5 squared times 11 times 19. And so when we put these together, you just add them together. So 3 plus 1 is 4, so 2 to the 4 times 5 cubed times 7 times 11 cubed times 19. And you notice that, of course, this is still a prime factorization. And multiplication is much, much easier when you're in this sort of prime factorization regime, because you can just add together the powers. And in fact, this is a general rule for multiplication, and so let's write it out in sort of general mathematician language, which is if we let n be equal to 2 to the a sub 2 times 3 to the a sub 3 times 5 to the a sub 5, and so on. So you have the coefficients for each of the powers in the prime factorization for both n and m. Then the product, n times m, well, you just add together all of the various coefficients. I just noticed something that, so I noticed that a few people have really, really short names in this chat. If you're using one of those, please let me know, because I basically tried to do your participation mark by looking at your names in chat and then matching them to the your name or your username on Quirkus. So if you're using a different handle, please just email that to me later, or you won't get participation points. But if your handle has your name in it, I will probably figure it out. Anyway, so we have lists, and we can use this. So we already used this in the previous example, right? So we had 33,880. Well, that's equal to 2 cubed times 5 times 7 times 11 squared. And that's equal to, well, if you write this out including the 0 coefficients, that's 2 cubed times 3 to the 0, because that's just equal to 1, times 5 to the 1, times 7 to the 1, times 11 squared, times 13 to the 0, times 17 to the 0, times 19 to the 0. And 31,350 is equal to 2 times 3 times 5 squared times 11 times 19. So that's equal to 2 to the 1 times 3 to the 1 times 5 to the 2 times 7 to the 0 times 11 to the 1 times 13 to the 0 times 17 to the 0 times 19 to the 1. Okay, and so when you multiply these together, so product, you just add those together. So again, that's 2 to the 1 plus 3 times 3 to the 0 plus 1 times 5 to the 1 plus 2 times 7 to the 1 plus 0 times 11 to the 2 plus 1 times 13 to the 0 plus 0 times 17 to the 0 plus 0. Oh, did I get that wrong? No, I didn't. Okay. How am I figuring this out? Times 19 to the 0 plus 1. Okay, yeah, so this is important. So basically, this step I'm giving you. So, I will show you how to figure this out in a moment. But for now, we're just saying that we know this prime factorization. So this is given. So we know these prime factorizations. And then what I'm doing is I'm rewriting it out with all the coefficients, including the zero coefficients. So you'll notice that I have a 3 here, but no 3 here, which means that the coefficient of that is 0. And then once you have all these coefficients, then if you get the product of the two of them, you just have to add together the coefficients. So for example, this here is, oh, sorry, did I just, okay, come on. This here is just 3 and 1, and so this is 3 plus 1. And the other, oh, actually I should have 3 plus 1, not 1 plus 3. Sorry about that. Does that sort of make sense? So all you're doing is you're adding together the coefficients if you're multiplying together the numbers in a prime factorization. Does that make sense? Okay, so let's have you all try it out. Okay, so that's all right. Don't worry, we're going to go through this again and again. So let's have you all try it out, and hopefully it'll be a little bit make a little bit more sense with easier numbers, since these numbers are really quite big and it's easy to get lost. So let's have you all try it out. So I'm going to give you some prime factorizations. So I'm just telling you in advance, this is what these numbers are equal to. Okay? And then what I'm going to want is I'm going to ask you, what is the prime factorization of the following? What is 120 times 132 as a prime factorization? Okay, so we have a lot of people who are guessing B. And let's actually sit down and work this out, and work this out slowly, since I know some people are still a bit confused. So we have 120, which is equal to 2 cubed times 3 times 5, right? And then we're multiplying that by 132, which is 2 squared times 3 times 11. And remember, we have a lot of different prime, we know how to multiply together pairs, right? When you multiply together pairs, you add them together. So this is 2 to the 2 plus 3 times 3 to the 1 plus 1 times 5 times 11, right? And so then that's going to be equal to 2 to the 5 times 3 squared times 5 times 11. Does that help? For those who were confused a little bit earlier? Yeah, so what you have to do is you just add together the powers. So let's try another one. What about 132 times 189? Okay, and again here, we're just adding together the powers. So this is going to be equal, so that's the bottom two. So that's going to be 2 squared times 3 cubed times 7 times 11. Actually, oh, sorry, 3 to the 4th. Because there's a 1 and a 3 there. Actually, wait, did I do this wrong? Everyone's answering A. Okay, let's see. So what has gone wrong? Let's walk through that slowly, Len, because something has clearly gone wrong. So either I made so given that everyone seems to think it's A, I probably made a mistake, but let's walk through that. So 132 is 2 squared times 3 times 11, right? And 189 is 3 cubed times 7. Okay? So once we have that, that's equal to 2 squared times 3 to the 4th power times 7 times 11. Oh, okay. The answer is A. I just was messing things up. So the answer is indeed A. Okay, good. Glad you guys are all well ahead of me. So given that, let's go ahead and try the last one here, which is, let's say, 120 times 189. So this is equal to 120, so there are 3 of them, 3 2's, 2 cubed. There are 4 3's times 5 times 7. And so the answer here is going to be C. Okay, great. It seems like you guys now know what's going on. You just add together the powers. So, and this is just using the same rules of powers that you guys are having to study for, say, question 2 on your quiz today. Or not today, but this week. Okay, so if you have a prime factorization, that makes multiplication easy. Well, that should also make how do you guys calculate so fast? So in this, I mean, it's just a matter of practice, and you do need to practice, and this is something you need to learn how to do quickly on the quizzes. So in this case, you're just doing 2 times 3, and 3 times 1 plus 3, and 5 and 7. Because you're just starting with each of these pieces. So the way to think about it is you're breaking up 120 into 1, 2, 3 times 5 times 3 times 3 times 3 times 7. And so you're just adding together all of those pieces, and you're counting them that way. Okay, but division is also easier via factorization, because division is just the opposite of multiplication, right? So it's just the opposite, and you can use the power rules to show that division of prime factorizations is the same as subtracting exponents. So if you have n and m in the same format as before, then n over m is just the subtraction of the exponents, and n is divisible by m precisely when a to the a2 is greater than or equal to b2, and a3 is greater than or equal to b3, and so on, when all the exponents are greater. So let me give an example of that. I'll give a couple of examples. So if we start off with our big number, 33,880, divided by 31,350, well, that's equal to, and this is just using the prime factorization we already know, that's 2 cubed times 5 times 7 times 11 squared, and the bottom is 2 times 3 times 5 squared times 11 times 19. Okay? And now this here is just exactly the same type of thing that you guys have been doing in part 1 when we went over like powers and exponents. So this happens to be equal to, there are a couple different ways of writing this. One way is you'll notice that the tops you have 3 2's on top and 1 2 on the bottom, and so those cancel out, so you end up with 2 2's on top. In terms of 3's, you only have 1 on the bottom, so that just stays there. 5's, you have 2 on the bottom and 1 on top, and so you're left with 1 of them. 7, there's just 1 on top. 11, there are 2 on top and 1 below, and so you're left with just 1 on top. And the 19 is just on the bottom. Or if you want to use the formula we had earlier, this is just 2 to the 3 minus 1 times 3 to the minus 1 times 5 to the 1 minus 2 times 7 times 11 to the 2 minus 1 times 19 to the minus 1, which is equal to 2 squared, 3 to the minus 1, 5 to the minus 1, 7 times 11 times 19 to the minus 1. Okay, and of course these two are equal. Because dividing by a power is the same as multiplying by the negative version of that power. And similarly, if you had, so this is going to be pretty easy, so it's a little bit silly to write this one this way, but we're going to do it this way just to give you an example. So we obviously all know the answer to that is 2, right? 120 divided by 60 is equal to 2. But another way we could see that is by writing out the prime factorizations. This is 2 cubed times 3 times 5, and this here is 2 squared times 3 times 5. And so then this is equal to 2 to the 3 minus 1, 3 to the 1 minus 1, and 5 to the 1 minus 1, which is equal to 2 times 3 to the 0 times 5 to the 0, which is equal to 2. Okay, so division is just the opposite of multiplication, and I'm going to have you try that out now, per usual. So let's have you all try it out. Let me reset the polling. Oh, how did we get 2, 3, and 5? Oh, we're not there yet. So, I haven't told you how to do a factorization yet. I mean, I've sort of told you how to do a factorization, but I haven't really told you how to do a factorization. I'm just giving these to you right now. And then in a little bit, we'll show you how to actually get these factorizations. Oh yeah, no worries. Yeah, please don't apologize for asking questions. I love questions. So, for the following pairs of numbers, I want to ask you if these things are divisible. So is n divisible? Say if n is divisible by m. Okay, so it looks like everyone's saying yes. And, well, how do we see this? Well, you can just write this out, right? N divided by m. Well, that's equal to 2 cubed times 3 times 7 squared times 13. And m is 2 squared times 3 times 7. And, of course, the numbers on top for the same coefficients are all bigger. And so this is equal to 2 times 7 times 13, right? So A, yes. Okay, so that one was straightforward. Let's do another one. What about these two? Okay, so most people are saying no. And let's work it out. So n divided by m. So what do we have on top? We have 2 to the 4th times 11 times 19. But what do we have on the bottom? 2 cubed times 3 times 11. And so even when you cancel everything out, when you simplify everything, you're left with 2 times 19 with a 3 on the bottom. And of course, you can't get rid of that 3 because 3 is a prime. So division factorization only works if the numbers n and m are divisible. So when you start, so you end up with something that's not a whole number if the numbers aren't divisible when you divide, obviously. And the way you can check this is just by checking to see if all the powers on top are bigger than the powers on bottom. And then that'll tell you if it is divisible. But of course, you can still use this even if it's not. When you're simplifying a fraction, this is what you're doing in effect. So if I start with the fraction, say 12 over 9, when I simplify that, that's really saying this is 2 times 2 times 2 times 3, and this is 3 times 3. You cancel out these 3's, and you're left with... Oh, wait, sorry. I had one too many 2 there. So you're left with 4 thirds. So that's really what you're doing when you're simplifying fractions. But yes, of course. So if they're not divisible, then you end up with something that isn't a whole number. And that's exactly what we're doing here. Okay, so let's give you guys one more of these. So let's say that n is equal to 2 squared times 3 times 7 squared, and m times 13, and m is equal to 2 to the cubed times 3 times 7. Okay, yeah. And so this turns out you don't even have to check the entire thing, because you notice that this thing is bigger than that. So 3 is greater than 2 in powers of 2. And so the answer is indeed no. Okay, so let's see. So now we know how to use factoring for multiplication and division. In fact, it makes multiplication and division much easier. But it turns out there are other sort of more advanced uses of factoring, which we'll let's talk about now. So how many how many numbers divide 24? So how would you go about solving this? How many numbers divide 24? Does anyone have any guesses? Okay, yeah, so some people know, have just written out the numbers. And, okay, so you guys listed them all out by hand, right? So you figured out what all the numbers are that divide 24, or you're trying to list them all out. And if you list them all out and you're really careful about it, then you can count them, right? And so it turns out that the answer is indeed 8. And let's walk through that because, so 24 divided by 1 is equal to 24. 24 divided by 2 is equal to 12. 24 divided by 3 is equal to 8. 24 divided by 4 is equal to 6. 24 divided by 5 is equal to 4 remainder 4. 24 divided by 6 is equal to 4. 24 divided by 7 is equal to 3 remainder 3. 24 divided by 8 is equal to 3. Did I count these wrong? No. Okay, I did this right. Okay. 24 divided by 9 is equal to 2 remainder 6. 24 divided by 10 is equal to 2 remainder 4. 24 divided by 11 is equal to 2 remainder 2. 24 divided by 12 is equal to 2. And then the rest of these, 24 divided by 13, all have a remainder. So that's 1 remainder 11. 24 divided by 14 is equal to 1 remainder 10. And so on, all the way to 24 divided by 24 is equal to 1. And so which of these work? 1, 2, 3, 4, 5, 6, 7, 8. Okay, that was rather painful, right? And it was really easy to miss something. And it turns out the problem is that counting up all of these is slow and time-consuming. So now the question is, can we do better? And of course, the answer to that is yes, because otherwise I wouldn't be talking about all this. So how do we do better? Well, we can count the divisors by making use of factorization. So let me explain all this. So the first thing I'll notice is I'm first going to walk through a factorization. So since that was a question someone had earlier. So if I have 24 and I want to factor it, that means I need to break it up into smaller pieces over and over again until I get prime numbers. So well, what's 24 equal to? Well, I know how to break that up. So this turns out to be, let's say 4 times 12. Sorry, not 4 times 12, 4 times 6. Actually, no, let's do 2 times 12. So the first thing you might notice is that it's even. And if it's even, that's easy, right? You know you can divide it by 2. So then you do this, and that's equal to 2 times 2 times 6. It's equal to 2 times 2 times 2 times 3, which is equal to 2 cubed times 3. Okay, so we now have a prime factorization. So now how do we use this to get the number 8 in terms of the total number of divisors? Well, the way this works is, notice that all divisors must be of the form 2 to the a times 3 to the b, where a is less than or equal to 3, and b is less than or equal to 1. Or equivalently, a can be either 0, 1, 2, or 3, and b can be any one of 0 or 1. And why is that? Because of the division fact that we just talked about. So when we talked about division, n is divisible by m precisely when all the coefficients, or all the powers are greater, right? So in this case, we need all the powers to be greater. And we know the powers are 3 and 1. And so we need those to be greater than their respective powers in the divisors. And so you end up with things like, so you can list them all out, and you have both of these possibilities. So you have things like, let me put this in orange. You have 2 to the 0 times 3 to the 0, 2 to the 1 times 3 to the 0, 2 to the 2 times 3 to the 0, 2 to the 3 times 3 to the 0, and 2 to the 0 times 3 to the 1, 2 to the 1 times 3 to the 1, 2 to the 2 times 3 to the 1, and 2 to the 3 times 3 to the 1. And this is 1, 2, 4, 8, and 3, 6, 12, 24. Okay, so we end up with 8 possibilities. But we can actually do slightly faster, because we know that there are 4 possibilities here and 2 possibilities there, and so the final answer is just 4 times 2, which is equal to 8 divisors. Okay, so that was several different steps in logic. Did that make sense, or is anyone confused about that? Okay, so let's give another example. And let's walk through this together. How many numbers divide 756? Well, the first thing you have to do, so step 1 is you have to factor 756, and step 2 is then you multiply together 1 plus each of the powers. This is a much bigger number, so figuring out the number of divisors would be really painful by hand. But what we can do is 756, well, that's equal, well, we know that's even, so that's equal to 2 times 378, and we know that's even, so that's equal to 2 squared times 189. And one thing you might notice is that 189 is divisible by 3. You can, of course, add together the digits and check, and that's one way of figuring that out. So that's equal to 2 squared times 3 times 63. And this, 63 is also divisible by 3, so that's equal to 2 squared times 3 squared times 21. And that's equal to 2 squared times 3 cubed times 7. Or 7 to the 1 if you want to write it that way. And then for each of these, for the 2's, you can have the possibility of 0, 1, 2, or 2. So you have 3 possibilities. So you have 2 plus 1 possibilities for 2. For 3, you have 0, 1, 2, 3. So you have 3 plus 1 possibilities for 3. And for 7, you have 0 or 1. So you have 1 plus 1 possibility, which is equal to 3 times 4 times 2. Total possibilities, which is equal to 24 different divisors. And in fact, we could list out those divisors if we wanted to using the prime factorization. So for example, you have like 2 to the 1 times 3 squared times 7, which is equal to 18 times 7, which is equal to 70 times 56. 70 plus 56, which is equal to 126. Did I do that right? Times 6? Yeah, so is a divisor. Okay, and so this gives us a quick way of computing the total number of divisors of a number. Once you have the prime factorization, you can count up all the divisors by just multiplying together 1 plus the powers of the prime factorization. So, well, let's have y'all try it out. How many divisors does 384 have? Okay, so we're getting a couple different numbers. And we'll give you all a moment to figure this out. Make sure you're actually doing a prime factorization and not just following along with whatever the first person answered. Okay, so it looks like a lot of people guessed that the answer was C, 12. Well, let's actually solve this now. So, what is 384? Well, you might notice that this looks like it's divisible by 2, right? Because it's even. So it's divisible by 2. So if it's divisible by 2, that means this is 2 times 192. That's still divisible by 2. It's equal to 2 squared times 96. That's still divisible by 2, so that's 2 cubed times 48. Still divisible. 2 to the 4th times 24 equal to 2 to the 5th times 12 is equal to 2 to the 6th times 6 is equal to 2 to the 7th times 3. And when I say 3, I really mean 3 to the 1. And so then you add up that, so that's 7 plus 1 times 1 plus 1 is equal to 8 times 2, which is equal to 16. So the answer here is actually D. Okay, did that make sense to people? It looked like a lot of people got that wrong. So, I don't have any other examples here, but this will be something that you should practice. There are some problems on the, yeah, so there are some practice problems on the ungraded problems. I know that you guys will be all busy worrying about your quiz this week, but they are on there. And there will be problems like this on the assignment, which has also been posted. So just be aware of that. Oh, I should remind you, the assignment's been posted and is due at a week from Friday. So assignment 2 has been posted. So FYI. Oh, why did I multiply by powers of 2? Oh, that's a really good question. And I I skipped a couple steps. So let me walk through this a little bit more slowly. So this is 2 times 192, that's fine, right? Well, what's that equal to? That's equal to 2 times 96, right? Because 192 divided by 2 is 96. So 2 times 96 is equal to 192. And then I collected together these two powers to give a power of 2. So that's 2 to the 2. And similarly, when we had this here, that was 2 squared times 2 times 48. And then I collected together the power of 2 again, back in. And this here, so you get 2 cubed times 48. And this here is 2 cubed times 2 times 24. So basically, each time I was moving one of the powers of 2 from the right piece to the left piece. Also, how did you end up with 7 plus 1 and 1 plus 1? That's a very good question as well. So what's going on here? So we know that this is our number, right? 2 to the 7 times 3 to the 1. And so that means that in a divisor, so say D is a divisor, then we know that all the exponents have to be smaller, right? So D is equal to 2 to the A times 3 to the B, where A is less than or equal to 7, so A is less than or equal to 7, and B is less than or equal to 1, right? How many numbers are there that are less than or equal to 7? So there's 0, 1, 2, 3, 4, 5, 6, 7 are less than or equal to 7. But of course, since you're adding the 0, so there are 8 numbers. So this is 8 numbers. So 8 different possibilities for the power for A. And then for B, you have 0 or 1, which are both less than or equal to 1. So you have 2 numbers. And so that's why you multiply together 8 times 2. To get the total number of divisors. Okay. So I have a couple more minutes. Let's talk about something we've seen before, just in a slightly different way. Okay? Am I okay to move on? Okay. Let's move on. So, what is the greatest... So, we have talked about greatest common divisors in the past, right? And we used the Euclidean algorithm for all of these. We used the Euclidean algorithm for all of these. Why did we add 1 to each? Because you also have to have is it a coincidence that we multiply the exponents by... You add the exponents by 1... you add the exponents plus 1 in the final step because you also have to count 0. So you're also allowed to have a 0 exponent. You're allowed 0, 1, 2, 3, 4, 5, 6, 7 if the maximum exponent on the 2 was 7 in the original number. Okay, but now let's take a look at factorization. So we already did this using the Euclidean algorithm, but it turns out that if you know how to factor, things can be easy. I noticed on the Discord that some of you were like, well, you just use factoring to solve it on the assignment, which was fine, but on the quiz, you do need to use the Euclidean algorithm. But there is this other way that we're now going to learn about using factorization. So notice that if D divides n, then the prime factorization of D must have exponents less than or equal to the prime factorization of n. Right? So that was one of our points of division. So division by factorization. Yeah, no, that's fine. You can just keep me on the decoy, and you can, I'm sure you guys have your own ways of doing things as well, but yeah. So if you... But anyway, so I noticed that some of you were using factoring to solve it instead, which is, of course, a different way of solving greatest common divisors. And that's the way we're going to be talking about now. Because you can do division by factorization, and that gets you, when you do that, you subtract out the exponents. And so it only works whenever all the exponents are less than or equal to the prime factorization of the other number. So wait, sorry, where was I? Let's go back to the greatest common divisor. And so therefore, if d divides two different numbers, both n and m, then all the exponents must be less than or equal to those in both n and m. Right? So if it's a divisor of two different things, then it has clearly the exponents have to be less than or equal to the exponents in both of them. So then the greatest common divisor thus has exponents exactly equal to the smaller of the exponents in n and m. So let's give an example of that. So if you have 24, oh, sorry, let me, let's throw it on there. So if you have 24, that's equal to 2 cubed times 3. Okay? So, and let's say 54 is equal to 2 times 3 cubed. Well, one way of solving that is by using the Euclidean algorithm. So one way of solving that is 54 is equal to 24 times 2 plus 6. So the greatest common divisor is also the same as the greatest common divisor 24 and 6. And 24 is equal to 6 times 4. So that's just equal to 6. Another way of solving that is you can say that the greatest common divisor of 24 and 54 is equal to, well, what's the largest exponent? So if we put 1 here for the largest exponents, then you have 2 to the 1 times 3 to the 1, which is equal to 6. So if you can factor, then you can also figure this out by just looking at the greatest, the smallest of all the exponents for each term. But be a little bit careful. So for example, if we had, say, 21, which is equal to 3 times 7, and let's say we had 14, which is equal to 2 times 3, then you have to be a little bit careful because this is the same as 2 to the 0 times 3 to the 1 times 7 to the 1. And this is equal to 2 to the 1 times 3 to the 0 times 7 to, times 7 to the 1. And so the greatest common divisor of 21 and 14 is then going to be equal to 2 to the 0 times 3 to the 0 times 7 to the 1, which is just equal to 7. Okay, so this is a different way of doing doing greatest common divisor, is by knowing the factorizations. And we can do the same kind of thing for the least common multiple, and the logic is the same. So suppose that m is a multiple of a. Well, then the prime factorization of m must have exponents greater than or equal to the prime factorization of a. So if something is a multiple of both a and b, then all the exponents must be greater than or equal to those in both a and b. So the least common multiple, the smallest one, has exponents exactly equal to the largest of the exponents in both n and m. And so, for example, if you have 24 is equal to 2 cubed times 3, and 54 is equal to 2 times 3 cubed, then the least common multiple of these is equal to 2 cubed times 3 cubed, which is equal to 8 times 27, which is equal to 216. And you can also check this manually, several different ways. But one of the ways of showing it is, well, you can just check them. 24, 48, 72, 96, 120, 144, 168, 192, and 216. And the other one would just give you 54, 108, 162, 216. Okay, so factoring gives you a somewhat easier way. If you know how to factor, then it's easy to find both the greatest common denominator, divisor, and the least common multiple. And I am running out of time, so I will end roughly speaking around here. I will end roughly around here, and next time when we come back, I'll talk about proving that the least common multiple times the greatest common divisor is the same as the product of the two original numbers. And now that we have factoring, we can actually prove this. You don't have to take it for granted. And that is where I think I will end this time. Unfortunately, I didn't get to the history of irrational numbers, but we'll talk about that on Monday. So with that, I will go ahead and end the recording. And I have office hours now, so if you have questions, I can hang around and answer questions that you guys might have. So I will see you guys all on Monday.